Good morning everyone, I am Mr. Ish. Thank you for joining me for this video. Ironically, everything I'm showing you here in this particular video is end of pre-calculus topic and end of calculus 1. You'll see this in calculus 1 at the end of the book. You'll see this in pre-calculus at the end of that specific textbook. And it's all relevant. It's to do with the motion of a particle and to do with parametric equations. You have in this question right here parametric equations, two of those. Everything here is, as you're seeing, in three variables, x, y, and t. The parameter here is t. When you are looking here, you're looking at x is equal to 2 cosine t plus 3. And then likewise we have y is equal to 2 sine t plus 1. This clearly defines the restrictions upon t, which will help us orient the curve in terms of its direction. Because when we're given a curve is no different than any other curve. But when you're talking about a parametric curve, you're talking about direction of that, a movement of a particle along a given direction. And we have to do all of that from this particular presentation. We will look at two questions. This right here is question number 1. When I'm looking at something like this with sines and cosines, x's and y's, always in the back of your head be thinking about that trigonometric identity, sine square x plus cosine square x equals 1. And when you're thinking about that, you should usually be thinking about a form of a circular shape. It doesn't have to be a true circle because you can have ellipses come about, but it can be either a circle or an ellipse. When I'm seeing this, the first step I want to do is take the constant on the other side. X minus 3 is equal to 2 cosine t. When I'm doing here, I'm exactly the same. Take the constant over there, 2 sine t. Y minus 1 equals 2 sine t. Now take the coefficients on the other side. I have an x minus 3 over 2 is equal to cosine t. You know we can parenthesize the t, but we don't have to. And we have sine t. Now look, when you're looking at something like this, the denominators are equal. That clearly tells you whatever shape you're looking at, the circular shape, it will have two transverse axes perpendicular to each other, but they'll be equal. Since the major and the minor axis are irrelevant here, we're looking at a circle because these numbers are the same. A good step here is to square this, and likewise everything else I'm squaring. And then you'll have x minus 3 whole square over 4 is equal to cosine square t. And then from here you'll have y minus 1 whole square over 4 is equal to sine square t. You can literally combine these things in the following way. X minus 3 whole square over 4 plus y minus 1 whole square over 4 is equal to 1. Why can I do that? Because this is equal to this and that's equal to that, and together sine square plus cosine square are always equal to 1. Hence their substituents are also equal to 1. And this makes sense. This right here is a 4. It looks messy, but it's a 4. What do I do next? I take the 4 onto the other side. I have an x minus 3 whole square plus y minus 1 whole square is equal to 4. I have a center here for this circle to be 3, 1. I have a radius here to be 2. This right here restricts the movement of the particle from 90 to 270 degrees, but we can still draw it out. We're looking here at 1, 2, 3 and a center here. If I have a radius 2 in all dimensions, it's going only 2 units above, 2 units below. You know you have 1 point here, 1 point here, you'll have 1 point right here, and then you'll have another point here, and you'll have a circle develop. This is not accurate depiction here of what's going on because we have to put everything now with respect to the movement that is created, the orientation of this parametric curve. We have to do that. I am going to erase this because you don't need it, because the better equation form is right over here. Now let's talk about the orientation. We have a given point on this circle. This point always has the value as you see right over here. Any point on this circle can be defined in terms of an x value and a y value, which I'm putting down for you right here. Now the start point over here is exactly what you see right here, pi over 2. When we put pi over 2 in this right here, we get 2 cosine pi over 2 plus 3 comma 2 sine pi over 2 plus 1. When you do this computation, you're getting a 3. But when you're doing this computation, you're getting a 3. So that tells you this 3 comma 3 represents your very first point. Your first point in terms of movement. So that's my start. My next point I want to pick is, I want to pick only those points which are in this my start, this my end, and I'll pick one point in between. What's that one point I want to pick in between? Which is between 90 and 270. You can't go wrong with pi because that's an intermediate value. Remember, the orientation of your parametric curve or the direction is always determined in terms of increasing t values. In this direction, we're increasing the t values. When I'm looking at this, I'm looking at a minus 2 plus 3, which is a 1. When I'm looking at this, I'm seeing a 1 comma 1. When I'm looking right here, here's my second point. It's on the curve. It's my second point. It's a legitimate point. Now I'm going to look at my last value because I'm still trying to determine the orientation of this parametric curve. My last value I want to think of is 3 pi over 2. That's exactly what I'm doing. This right here is 0, but you still have a 3. This right here is a minus 2 plus 1. Minus 2 plus 1 is a minus 1. 3 comma minus 1. 3 comma minus 1. Here's my third point. Clearly, the orientation we've determined. This was my first, this was my second, this is my third. So I know everything is right over here, going in this direction, as you see, in a counterclockwise direction. Technically, if we are looking at everything here with regards to this constraint, our start is right here and our end is right here in a counterclockwise. It starts here from this value 3 comma 3, and the particle will move all the way up to value 3 comma minus 1, then it will stop, and that right there will be your answer. In a counterclockwise direction, here's my start, here's my end, the particle has moved that amount of distance, and that brings us right here to the end of this question. You can see how everything has developed here with regards to a circle having a radius, and then the increasing t values led us towards the orientation of this parametric curve. The curve is really from S to E, from my start to my end, in a counterclockwise direction. Our second and last question is exactly what you see here. X is equal to 5 sine theta, y is equal to 2 cosine theta. We have a restriction over there. The movement is occurring only from minus pi to 5 pi. But here the parameter is a theta. The angle theta in terms of radians is our parameter. When you're looking at this again in terms of sine and cosine, you are thinking either circle or you're thinking ellipse. But before we do anything, consider this. From 5 pi to minus pi, what is that? A difference of 6 pi. What's a normal period of a sine and a cosine? The normal period is going to be 2 pi. In the normal sine and cosine, as you see right here, you have a coefficient of each of these angle radians to be 1. Remember, 2 pi over b represents a period. Here you have 2 pi over that coefficient 1, which is 2 pi. The normal period I'm seeing here is to be 2 pi, but the particle is going to move over that distance of 6 pi. What does that tell you? If you have a normal period 2 pi, but we're moving through 6 pi, we're looking here at 3 turns. 3 turns. The particle is going to do 3 turns. We don't know if it's clockwise, counterclockwise. We don't know if it's a circle or if it's an ellipse, but whatever it is, it's going to do 3 turns. 6 pi divided by 2 pi, 3 turns. Now, take the coefficients on the other side. You have x over 5 is equal to sine theta, and likewise here, y over 2 is equal to cosine theta. Now, look, we have sines and cosines, but when we do look at the denominators, we don't have same numbers. That's going to be a problem because it's no longer a circle. You know you can have a major and a minor axis. And when you're thinking about major and minor axis, but you're thinking with sine and cosine, you're having an ellipse. You're going to have an ellipse develop out of here. And you'll see it x squared over 25 plus y squared over 4 is equal to 1. Why? Because it was equal to sine squared theta plus cosine squared theta. Independently, sine squared theta, cosine squared theta equals 1. But each of these is equal to a substituent which comes into the same format, and it's equal to a 1. You might as well erase this because it's irrelevant now. So we have x squared over 25 plus y squared over 4 equals 1. It looks very much like x squared over a squared plus y squared over b squared is equal to 1. A horizontally oriented ellipse. A is equal to 5, b is equal to 2. That's exactly what it is. Let's draw this ellipse. You have a vertex plus and minus 5 comma 0. We don't have to be too accurate. Here's my vertex 1, here's my vertex 2 at 5. We have a minor axis endpoints at plus and minus 2 comma 0, 2 minus 2. Connect these. We don't have to be too accurate here. Again, I'm saying that because we're just getting the orientation. Our main goal here is to describe the motion of the particle. We know the particle will move 3 turns. But we also know we're dealing with an ellipse which is horizontally oriented. Now the only question remains, are the 3 turns in a clockwise or in a counterclockwise direction? And that is the item to be determined. For any point on this ellipse curve, that point has an x and a y value which is described exactly as you see here by means of the parametric equations. That point has an x value 5 sine theta, it has a y value 2 cosine theta. When I'm looking at these, I don't have to go through the entire range of values. I can just go through 3 values, and I'll do minus pi, and I'll do, how about we'll do minus pi over 2, and then we'll do 0. When I'm putting minus pi over here, I'm going to get a 0, comma, I'm going to put a minus pi over here, I'll get a minus 2. 0, comma, minus 2 will represent the first point of that very first turn, which is going to start. When I put a minus pi over 2, I'm going to get a sign of minus pi over 2 with that 5 is a minus 5, but I'll get a 0. Minus 5, 0, that's my second value. When I put a 0 over here, I should not have put a minus here, minus 0, plus minus 0 is still 0. Anyhow, minus pi over 2, 0. When I put 0 over here, I'm getting a 0, comma, 2. That's my third point. That clearly tells me I'm moving in a clockwise direction. This entire turn of this particle will be in clockwise direction, but not a single turn, it'll be 3 turns. So we do have, as we have determined, 3 turns. They're all going to be in a clockwise direction, but just keep in mind this: the starting point is exactly 0 comma minus 2. 0 comma minus 2 is my start point, and it will also be my end point, 0 comma minus 2, because I'm starting in here, I'm doing a 1 turn, then I'm doing another turn, then I'm doing a third turn, all in a clockwise direction. 3 turns starting and ending at the same point, 0 comma minus 2, because that represented the start of that restraint that is affecting your parameter. But remember, in this question, our parameter is a theta. We have 3 turns, we have an ellipse, everything here is in a clockwise direction. The previous question had a circle develop, everything was a counterclockwise, but as you saw in that, the movement of that particle was very short, like a half a turn only. From pi over 2, it started, I believe it started from that value 3 comma 3, and then it went up to 3 comma minus 1. If I remember correctly, that was a movement, but it was a half a turn only, but that was counterclockwise. Anyhow, the 2 questions have been laid out for you: circle and an ellipse, everything here sine and cosine as you see. And that's it for this video. Thank you for watching.